Okay, so now we know how differentiation acts with respect to addition, subtraction, constant multiples, multiplication, division. So we know quite a bit about differentiation. We also know how it acts on polynomials and other powers of x, trig functions, and exponential functions. How else can we build functions? Well, we can compose functions and we can invert functions. The first thing we're going to look at is the topic of section 3.4, which is composing functions. And the rule that tells us how to differentiate the composition of functions is called the chain rule. So the question is, how does differentiation interact with function composition? The chain rule. And what the chain rule says is this: if I have two functions composed, f is the outer function and g is the inner function, when I take the derivative, I get f prime of g of x times g prime of x. The derivative of the outer function applied to the inner function times the derivative of the inner function. Why is this the case? Well, if we introduce some variables, typically we think of y as being the value of the function of x. Well, we have two functions here, so let's think of the inner function as sending x to some new variable u, and then the outer function f sends the variable u to the variable y. So y is f of u and u is g of x, so y is f of g of x. Then we can write the chain rule as this: dy dx, which is what we're looking to evaluate, the derivative of y with respect to x, is dy du, that's the derivative of f applied to g, times du dx. Now, this Leibniz notation for differentiation, I've said it's not really a fraction, but if we pretended for a second that, yes, these are fractions, then the du's would cancel and this would be equal. That's more or less what the proof is. We have to be a little bit more careful to show that this is actually true, but yeah, this works out. This is the chain rule. Great. Okay, so let's apply the chain rule. Now, the first couple of times I'm going to do this, I'm really going to explicitly use the chain rule, really write everything out carefully. Okay. The way I'm going to do it first is by decomposing the function, the function that is written as a composition of two functions. So let's differentiate capital F of x, which is the square root of x squared plus 1. What's going on here? I take x, I plug it into x squared plus 1, and then I take a square root. So the inside function here, my g of x, is going to be x squared plus 1. That's what's happening first. Then I take that and I plug it into the square root function. So my outside function f, I'm going to write it as f of u, where u is this sort of in the middle variable. It's the square root of u, which is u to the 1/2. Now I have to take the derivatives of each of these things. The derivative of g is just 2x. The derivative of f is 1/2 u to the minus 1/2. So now I have g prime and f prime, and I plug that into the chain rule. F prime of x, capital F prime of x, is f prime of g of x times g prime of x. So what is f prime of g of x? I plug g of x, which is x squared plus 1, into f prime. F prime is 1/2 of whatever to the minus 1/2. So since g of x is x squared plus 1, I get 1/2 of x squared plus 1 to the minus 1/2. Then I multiply by g prime, which is 2x, and I get this expression. You could go ahead and simplify it. I'm just going to leave it like this. You know what? Never mind. I'm going to simplify it. This becomes 1/2 times 2, cancels out. X squared plus 1 to the minus 1/2, that goes into the denominator. 1/2 power means square root. So I get x over the square root of x squared plus 1. Nice. All right, let's do another example. Let's let y be secant of e to the x. This is the sort of problem where it's pretty easy to see what the decomposition is. E to the x is clearly what's on the inside, and the outside is secant. So I decompose this so. G of x is e to the x. F of u is secant of u. Okay. So then y is f of g of x. It's secant of e to the x. Now I take derivatives. G prime is e to the x. E to the x is its own derivative. And the derivative of secant of u is secant u tangent of u. Okay. So that means that y prime, according to the chain rule, is f prime of g of x times g prime of x. Now this is a place where some people run into a little bit of trouble when they try to evaluate f prime of g of x, because f prime here is actually secant of u times tangent of u. When I plug g of x into here, I have to plug it in for both instances of u. So g of x is e to the x. That means I get secant of e to the x times tangent of e to the x. This thing right here. That is my f prime of g of x. Then I multiply by g prime of x. G prime is just e to the x. That goes right there. My final answer is secant of e to the x, tangent of e to the x, times e to the x. Okay, so for the next two examples, I'm going to try to illustrate two things. First of all, the order that we compose things in matters. If I have cosine of x squared, that's going to be different from cosine squared of x. So first we're going to do cosine of x squared. Second, I'm going to use the second way that I wrote down the chain rule. I introduced a variable u, which was the inner function of x, and then I let y be the outer function of u. And then I wrote the chain rule as dy du, du dx. So, the inner function is u. I introduce a new variable u, which is x squared. Okay, so since the inner function is u, I can write y as cosine of u, because x squared is u, y is cosine of u. Now I evaluate du dx and dy du. Du dx is the derivative of x squared, which is 2x. And dy du is the derivative of cosine of u, which is negative sine of u. So, f prime of x is dy du times du dx according to the chain rule. And this is equal to, well, dy du is negative sine of u. Du dx is 2x. Looks great, but I'm not done yet because u is just a variable I introduced to help me along in evaluating this. What I really care about here is x. X is the variable that I was looking at the beginning of the day. So I have to replace u with what it is, x squared. So my final answer is negative sine of x squared times 2x. Okay, so now let's see what happens when we differentiate cosine squared. Of course, cosine squared means the same thing when I write it like this, cosine squared of x. That means the quantity cosine of x squared. Okay, again, we're using the notation u and y. So u is going to be the inside function, u is going to be cosine. So that means that I can rewrite g of x as u squared. So I'm going to let y be u squared. That's the same thing as cosine squared. Now I need to figure out du dx and dy du. Du dx is negative sine of x. That's the derivative of cosine. And since y is u squared, dy du is 2u. So let's put these together. G prime is therefore, by the chain rule, dy du times du dx. Dy du is 2 times u. Du dx is negative sine of x. Okay, but we don't care about u. U is just a friend that we invited over to help us move. He's a subcontractor, whatever. No, we care about x. So u is cosine of x. We replace u with cosine of x. I decided to bring the negative out in front, so I get negative 2 cosine of x times sine of x. It's a lot different than our previous answer of negative 2x times negative 2. I don't remember what it was. Whatever it was. All right, so here's question 1. Differentiate y equal to e to the tangent of x. Do it nice and carefully. Use one of the methods we used before, introducing a variable u, or decomposing the function e to the tangent of x into two functions f and g, whichever you prefer. Maybe both.